So let us next solve the exercises on IVPs and BVPs, initial value and boundary value problems. So this is number 2. The differential equation you see here, it is given that its solutions are of this form. This is a one parameter family of solutions where C is the parameter or arbitrary constant. With this information, we have to solve these two IVPs, initial value problems. In both of them, the differential equation is same, but the extra condition, that condition, these initial conditions are different. So in this one, y of 0 is equal to 2. So all we have to do is substitute x equal to 0 and y equal to 2 and find the value of that constant. That will give us that particular solution, which will be the solution of this IVP. So let's see the solution to part A. Since y of 0 equals 2, so what shall we get from the one parameter family? So on this side you will have 2, and on this side if you substitute x equal to 0, x square plus c will become c and e to the power minus 0 will become 1. So the right hand side becomes c. So c is equal to 2, just that. So the solution, let me write like this, to the IVP is y equals x square plus 2 times e to the power minus x. Not only does this satisfy the differential equation, but it satisfies this condition as well, supplementary condition. So that is part A. And then part B. Here we have to substitute x equal to minus 1 and y is e plus 3. So e plus 3 equals minus 1 square plus c times e to the power minus of minus 1, or, so that means it is just e. Now if we divide both sides by e, then we are going to get 1 plus 3 over e, and the right hand side will be 1 plus c. So that way we get c equal to 3 over e. So the solution is, in this case, y equal to x square plus 3 over e times e to the power minus x. Okay, so that's the solution to the exercise. This, we have to show that, 3 boundary value problems are given. We have to show that the first 2 have solutions, but the third one does not have solution. So let me just write the BVPs, simply that, without writing much more. So the first one is the differential equation. So same differential equation, so I just simply write dE. And the boundary conditions are y of 0 equal to 0 and y of pi divided by 2 is equal to 1. Okay. So let's use these supplementary conditions and create 2 equations involving C1 and C2, and then we can solve them. So we will see parts B and C afterwards. Let's first solve this. Since y of 0 is equal to 0. So what shall we get if we substitute x equal to 0 here? This part will vanish because sin 0 is 0. Cos 0, however, is 1. So we will get C2. And what is this? This is 0. So the left hand side is 0 and the right hand side is C2. So actually we are already getting C2 equal to 0. What else? Since y of pi over 2 is equal to 1, so on this side we will have 1. What will happen here? Sin pi over 2 is 1 but cos pi over 2 is 0. So this time we will have C1. So that means C1 is 1 and C2 is 0. So the solution is y equal to sin x. That is the particular solution to this 2-point boundary value problem. Next, B. Same differential equation is same and the boundary conditions now are these. Y of 0 equals 1, but this time y prime, the derivative of y at pi over 2, that is also equal to 1. Oh sorry, not 1 but minus 1. Let's see what we get for this one. Solution. Since this time y of 0 is equal to 1. And just for our convenience, let me again write this. C1 sin x plus C2 cos x so that we can see. So y of 0 was what? C2. And C2 now is equal to 1. So C2 is equal to 1. Also, before we can substitute pi over 2 here, we need to know the derivative. So what is y prime? Y prime will be C1 cos x minus C2 sin x. Since this is equal to minus 1, so minus 1, that means y prime of this, on this side we have minus 1. You can write it on any side, but I am writing it the way I have written this equation. So now what shall we get? This term will vanish because cos pi over 2 is 0 and that one will remain, that is this is minus C2, or from this we get C2 equal to 1. Okay, so both C1 and C2 are equal to 1. So the solution is y equals sin x plus cos x. However, the BVP in part C is supposed to not have any solution. The differential equation, and these are the boundary conditions. Y of 0 is 0 and y of pi is 1. Okay. Since y of 0 is 0, so what shall we get from our, you can imagine here C1 sin x plus C2 cos x. So for 0 we only have C2, right? So C2 on the right side and 0 on the left side. So we are getting C2 equal to 0. However, if you now use the second supplementary condition, y of pi is equal to 1, so 1 on this side and C1 sin pi is 0, so again this term vanishes, plus C2 cos pi is minus 1, so you get minus C2 on this side, or C2 is equal to minus 1. But you can now clearly see that this is not possible. C2 cannot be simultaneously 0 and minus 1, and that is why this one is not solvable. This BVP has no solution. You can write the sentences yourself. Next, 6. And in fact, if you remember, this was precisely that problem that we talked about before, which at that time the author indicated that this has no solution. Now we can see ourselves why it has no solution. Next, what the IVPs are. There are two of them. A. So the differential equation is this: dy dx equals x square sine y, and the initial condition is y of 1 equal to 2. So according to how the theorem is stated, let us first call this side some function f of x comma y. Let this be x square sine y. So now we not only have to say something about f, but its partial derivative with respect to y. So let's calculate the partial derivative. It's pretty easy. So only this gets differentiated with respect to y. X squared remains as it is. So that you get cos y. Now you have to you have to have the fact that both the function as well as its partial derivative are defined and continuous in some domain, on some domain entirely, which contains the point 1, 2. Because of what the functions are, both these functions actually exist and are continuous throughout the two-dimensional plane, our R2. So there we can just choose any domain which contains that point. Conveniently, we can choose a disk, a circular domain with that as the center. Now, both f and del f del y are continuous on the following domain. Let me call it D1. R2, won't be able to write it fully here. X minus 1 square plus less than 1. This strict inequality ensures that this is an open set. Okay, so actually it's an open ball in R2, you can see that already. And of course it's connected as well, so it's a legitimate domain. Hence, that's it. By theorem 1.1, the given IVP has a unique solution. Some solution phi in an interval whose center is 1. So it looks like this. Let me call it H1 because we have to solve another problem. 1 plus H1, and that's why also I called it D1 because we are going to next consider D2. unique solution for some positive real number h1. Next, let us see b, which won't be as easy as this one. Dy dx equals y square divided by x minus 2, and the initial condition is y of 1 equal to 0. So this x minus 2 is there in the denominator. Let g of x comma y be y square divided by x minus 2, then del g del y is 2y divided by x minus 2. So both g and its partial derivative have that problematic term. Now, so a little figure will help us figure out where we are and what we have to avoid. Vertical line is what we have to avoid. Our point, however, 1 comma 0 lies here, halfway between these two lines. And we now want to choose a domain which contains this point, but that does not contain any portion of this line, because it's convenient to choose a circular domain. So why don't I choose this circle? What is the radius of this circle? The radius of this circle is 1 divided by 2, because this much is 1. Okay, so I am going to take that circle. Then whatever points x comma y you are going to take from within the circle, for those points x coordinate is not equal to 2, because those points lie on this line where x coordinate is equal to 2. So we do not have any problem with this denominator. That's it. So this will be our D2. G and del G del Y are continuous on the domain D2. So we want the radius to be 1 over 2, so it's square. So theorem 1 implies that the given IVP has a unique solution. Some solution, let me call it psi. 1 minus h2 comma 1 plus h2. First, so in spite of not knowing what the solution possibly is, we know its existence and even its uniqueness. That's the power of the theory. What else do we have this? So that is done, and then there is a part B also. Part B asks us to graph this solution in these three cases. 1, C equal to 2, C equal to 3. If you want, you can do it on graph paper, or a better option is to go to Google and type Desmos graphing calculator, and straight away you just write the equation there, it will give you the graph. In fact, you can draw all 4 graphs simultaneously. So these graphs essentially are just the integral, essentially means actually they are the integral curves of this differential equation, and the different members that you see here are for these specific values of the parameter C. Okay, so you just see the graph and see how the graph of this for the value C equal to 0, which is somewhat like this. I mean, on the left side, of course, it's just 0. On the left side of the origin, it's just the x-axis, and then it goes up like this. And as you take higher and higher values of C, that itself slides to the right. So, for example, for C equal to 1, it slides to the right. For C equal to 2, it slides even more, but the shape remains exactly the same. Okay, so you please see this thing, and that's just it in this chapter, in fact. So in the next chapter we can go and, next week we can go and start really the methods that will give us exact solutions of some specific first order differential equations that we are going to learn. For example, one of them is exact differential equation. Then you have linear differential equation. Many different types are there. So we will learn about them. And that will be all for today. And tomorrow we have our usual number theory upload. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.